What if the universe is older than we think? Not slightly older, not a rounding error in the timeline. What if the foundational number that the entire modern cosmological framework is built on is wrong in a way that requires pulling the framework apart and rebuilding it from the ground up? There are galaxies at the edge of the observable universe that should not exist, not metaphorically, not in the sense of being surprising or unusual. They should not exist in the way that a building should not be standing if the ground beneath it was never there. The James Webb Space Telescope has been returning images of the early universe for roughly 2 years now. What it is finding, consistently, in paper after paper from credentialed researchers at major institutions, is fully formed, massive, structured galaxies appearing in the first few 100 million years after the Big Bang. Galaxies that the standard model of cosmology says could not have assembled that much mass, that fast, in that amount of time. The math is specific, the predictions are specific, the observations are not close to matching them. This is not a story about one anomalous image, it is not a calibration issue someone is working to correct. Dozens of objects, confirmed across multiple observing programs, show stellar masses and structural complexity that require formation timescales the model says were not available. The universe, according to the standard framework, was still a hot, expanding plasma for the first few 100 million years after the Big Bang. Gravity needed time to pull matter into filaments. Small structures had to form first. Large ones assembled gradually, over billions of years, through a slow process of merging and accumulation. That is what the model predicts. That is what it has predicted for decades. The Webb results are not consistent with that picture, not at the margins, not in ways that small corrections can absorb. When results like this come back, there are two responses available to a field. One is to follow the data directly, to ask whether the model is wrong at a foundational level and to pursue that question wherever it leads. The other is to treat the anomaly as a problem with the measurement, the instrument, the analysis pipeline, or the efficiency parameters inside the model. The second response is easier. It does not require rebuilding anything. It preserves the structure that took 50 years to construct, and it is professionally far safer. What does that tell you about which response has been more common? The researchers who first saw these images used a specific phrase, universe-breaking galaxies. That phrase did not come from science journalists or from YouTube. It appeared in peer-reviewed commentary from the people who built the model. When the scientists most invested in a framework describe their own observations as universe-breaking, the honest response is not to assume they are being dramatic. Here is what the published data actually shows. Objects at redshifts of 10, 12, 16, and beyond. Stellar masses 10 to 100 times larger than any standard formation model predicts should exist at those distances and those times. Structural organization, including disk morphology and defined arms, that requires sustained, stable formation processes across timescales the early universe was not supposed to provide. These are not marginal detections. Several have been spectroscopically confirmed. The redshifts are not guesses. The distances are not soft estimates. The objects are where the telescope says they are, and they are as large as the telescope says they are, and the model cannot account for them. The gap has been sitting in the literature since 2022. Teams have published proposed fixes. None of them close it completely. Each one patches one problem and opens another, and the field has, with impressive consistency, described all of it using the word tension rather than the word falsification. The language is doing work there. Tension implies the model is under pressure but intact. Falsification implies it has failed a test. The researchers publishing these results know the difference. The choice of language is not accidental. What does it mean when an instrument returns observations that contradict the model not once but systematically at the highest redshifts across independent research groups over 2 years of continuous data collection? What does it mean when the field's response is to adjust parameters rather than to ask whether the parameter adjusting model is the wrong tool entirely? That is what this is about. Not speculation, not alternative cosmology blogs, the actual data coming back from the most expensive telescope humanity has ever built, and what it shows that nobody in the mainstream wants to say directly. Here is what the standard model of cosmology actually says, because you need to understand exactly what it predicts before you can understand why what Webb is finding is a problem. The model has a name, Lambda-CDM. Lambda for dark energy, CDM for cold dark matter. Those two components sit at the center of it, and we will return to them. But start with what the model actually describes, because the structure of the prediction is what makes the problem visible. 13.8 billion years ago, everything that exists was compressed into a single point of unimaginable density and temperature. The Big Bang is not an explosion in space. It is an expansion of space itself, carrying matter and energy outward in every direction simultaneously. In the first fractions of a second, the fundamental particles form. In the first 3 minutes, protons and neutrons combine into atomic nuclei. For the next 380,000 years, the universe is a hot, opaque plasma, too dense for light to travel through, too energetic for electrons to bind to nuclei and form stable atoms. Then the temperature drops far enough, electrons bind, atoms form, light travels freely for the first time. That moment is called recombination, and the light released at that instant is still traveling. We can measure it today. It is called the cosmic microwave background. So, after recombination, the universe is dark. No stars yet, no galaxies. Just hydrogen and helium drifting through expanding space, pulled by gravity into thin sheets and filaments. The density differences are small. The process is slow. Small concentrations of matter form first, pulling in more matter, growing denser, eventually triggering the nuclear fusion that lights the first stars. Those first stars are small by one standard, massive by another. They burn fast, explode, seed the surrounding gas with heavier elements. Over hundreds of millions of years, star clusters form. Over billions of years, those clusters merge into galaxies. Small galaxies merge into larger ones. Large ones merge into larger ones still. This is the core architecture of the prediction. Small first, large later, dual hierarchical bottom-up. That is not a vague philosophical claim. It is a quantitative prediction with specific timescales. The model says how dense the first structures should be, how large, how many, at what point in cosmic history. It says that at a redshift of 10, which corresponds to roughly 500 million years after the Big Bang, you should see small, irregular, early-stage galaxies, sparse, dim, not yet organized, nothing with the stellar mass of a mature galaxy, nothing with the structure of an established system. The math is specific. The predictions are on paper. They were made decades before any instrument could test them. Why was the model trusted so completely? Because it kept being right. The cosmic microwave background, mapped precisely by the COBE satellite in 1992, and then by WMAP, and then by the Planck satellite, matched the model's predictions with extraordinary precision. The large-scale distribution of galaxies at intermediate distances matched. The abundance of light elements in the universe matched the predictions from Big Bang nucleosynthesis. The accelerating expansion of the universe, confirmed in 1998 by two independent teams studying distant supernovae, led to the Nobel Prize in Physics in 2011. The model absorbed that result by adding dark energy, which is the lambda in Lambda-CDM. It kept working. Observation after observation came back and fit. This was not a model that survived by luck. It survived because it was built carefully, tested rigorously, and updated when the data required it. The physicists and cosmologists who worked on it over 5 decades were not naive. They knew the model was incomplete. Dark matter has never been directly detected. Dark energy is essentially a name for something we do not understand. But the framework held. The predictions matched. The confidence was earned. Here is the thing the model's success created, though. It created extremely specific predictions about the early universe that had never been directly tested, because no instrument could see that far with enough resolution to actually measure what was there. Redshift 10, redshift 12, the first few 100 million years. The theory made clear statements about what that era should look like. For decades, those statements sat in the literature unconfirmed and untested, not because anyone doubted them, but because the tools to check them simply did not exist. James Webb changed that. It was designed in part precisely to look at the early universe with the sensitivity and resolution needed to test these predictions directly. The first deep field observations began returning in 2022. The data started coming back, and the comparison between what the model predicted and what the instrument found was not a close call requiring careful statistical analysis. It was immediate. The researchers looking at the first images knew within days that something was wrong. Not a small discrepancy, not a calibration offset that could be corrected by adjusting one parameter, not the kind of result that generates a footnote and a follow-up proposal, the kind of result that produces a specific phrase in the published literature. The model was supposed to be confirmed by the first deep-field images from James Webb Space Telescope. Instead, those images started a crisis that the field is still in the middle of right now. The James Webb Space Telescope launched on Christmas Day 2021, and by the summer of 2022, it was returning images that immediately produced a specific reaction from cosmologists. Not wonder, not celebration, not the triumphant confirmation of predictions they had spent careers making. The reaction was concern. Quiet, careful, precisely worded concern from people who do not use language loosely. Because what the images showed was not what the model said should be there. Not slightly off, not within the margin of error that any new instrument needs to calibrate around, structurally, fundamentally wrong in a way that the researchers recognized immediately and could not easily explain away. To understand what Webb found, you need to understand what redshift means. Here is the short version. When light travels across an expanding universe, it stretches. The further it travels, the more it stretches. That stretching shifts the light toward the red end of the spectrum. Astronomers measure that shift as a number, the redshift value, written as z. A galaxy at z equals 1 is seen as it was roughly 8 billion years ago. A galaxy at z equals 10 is seen as it was when the universe was less than 500 million years old. Z equals 12 pushes that back to roughly 370 million years after the Big Bang. Z equals 16, if confirmed, puts you inside the first 250 million years of cosmic history. That is the territory Webb was designed to reach, and it reached it. What it found there is the problem. The standard model predicts the early universe in that redshift range should contain small, irregular, partially assembled structures. Protoclusters of gas collapsing under gravity, early stellar populations just beginning to ignite. The first hints of galaxy formation, not the finished product. Small, dim, disorganized. That is what the math produces when you run it forward from the initial conditions the model assumes. Webb found galaxies, fully formed, massive, with stellar populations large enough that forming them required timescales the model says were not available. Galaxies at z equals 10 with stellar masses approaching 10 billion times the mass of the Sun. Candidate objects at z equals 12 and beyond with structural organization that takes billions of years to build under the model's own physics. The universe at that age, under Lambda-CDM, had not been running long enough to produce what Webb was photographing, and Webb was not finding one or two of them. The field expected to find a handful of early massive galaxies, maybe as rare outliers. They found hundreds. The researchers who published the first analyses were not junior scientists prone to overclaiming. These were people who had worked within the standard model for decades, who understood its predictions better than almost anyone, and who used language accordingly. One description that appeared in peer-reviewed commentary called the objects universe-breaking galaxies. That phrase is worth stopping on. It did not come from a headline writer. It did not come from a science communicator looking for engagement. It came from cosmologists writing in technical literature, people whose professional training produces extreme caution with language, describing what their instruments were returning. When that community reaches for a phrase like universe-breaking, they are not being dramatic. They are being precise. Alison Lovell and colleagues published early analyses noting that the stellar masses observed were inconsistent with the expected distribution by a significant margin. Mike Boylan-Colchin at the University of Texas published a paper in 2023 laying out the problem quantitatively, showing that the most extreme objects Webb was finding exceeded what the standard model could produce even under the most generous assumptions about star formation efficiency. His conclusion was stated carefully and directly. The observations were in tension with Lambda-CDM at a level that small adjustments would not resolve. Here is what that means in practice. The model allows some flexibility in how efficiently early galaxies convert gas into stars. Push that efficiency to its physical limit, and the model can produce more stellar mass earlier than the standard parameters allow. Researchers tried that. It helped with some objects. It did not cover the most extreme cases, and it introduced its own problems, because a model tuned to its physical maximum in one parameter is no longer making a prediction, it is fitting a curve. That is a different activity. And even with efficiency pushed to the limit, galaxies at z equals 16 with the masses Webb was recording remained outside what the model could account for. The number issue compounds the mass issue. Finding one anomalously massive early galaxy could be a rare statistical event, a fluctuation in the initial density field that produced something unusual. Finding hundreds of them across multiple independent survey fields, across different instruments and teams, at consistent redshifts confirmed by spectroscopic follow-up, that is not a fluctuation, that is a population, and the model has no mechanism to produce that population on that timeline. What makes this different from previous observational surprises in cosmology is the directness of the contradiction. Webb was not finding something unexpected in a peripheral measurement. It was looking at exactly the period the model makes its clearest predictions about, the early universe, the era of first structures, the territory where Lambda-CDM's timeline should be most directly testable, and the test is returning the wrong answer, not ambiguously, not in a way that more data will clarify into agreement. The more data comes back, the more the pattern holds. When the people who built the model describe the observations as universe-breaking, the honest response is not to assume they are exaggerating. The PETM carbon gap has languished in the published record since the early 1990s. The Paleocene-Eocene thermal maximum, occurring approximately 56 million years ago, represents one of the most dramatic climate change events preserved in the geological record. During this interval, global temperatures rose by 5 to 8 degrees Celsius over a period spanning several thousand years. This rapid warming fundamentally altered Earth's climate system, ocean circulation patterns, and ecosystems across the planet. Yet, despite decades of intensive research, scientists have struggled to fully account for the carbon required to drive such substantial warming. The carbon budget problem emerged as researchers compiled increasingly precise measurements from multiple paleoclimate archives. Ice cores, sediment records, and isotopic analyses provided detailed information about atmospheric composition and temperature fluctuations during this period. However, when scientists calculated the total amount of carbon that would have been necessary to produce the observed warming, they discovered a significant discrepancy. The amount of carbon found in geological records fell substantially short of theoretical requirements. This deficit became known as the PETM carbon gap, a puzzling anomaly that has motivated substantial scientific investigation. Throughout the 1990s and early 2000s, the carbon gap remained a contentious issue within the paleoclimatology community. Different research groups proposed competing hypotheses to explain the missing carbon. Some scientists suggested that submarine methane hydrate releases could account for the additional carbon dioxide entering the atmosphere. Others proposed that massive volcanic outgassing events had injected carbon into the system more vigorously than previously estimated. Still others argued that the carbon might have accumulated through multiple smaller sources working in concert over extended periods. The problem proved particularly vexing because the PETM represents a natural analog for understanding rapid climate change. Modern concerns about anthropogenic carbon dioxide emissions gave the research heightened relevance and urgency. Understanding how Earth's climate system responds to sudden carbon injection has direct implications for predicting future climate scenarios. However, without resolving the carbon gap, researchers remained unable to construct fully confident models of the warming mechanism. Refinements in analytical techniques gradually improved the precision of paleoclimate measurements throughout the following decades. Researchers developed more sophisticated methods for extracting carbon isotope signatures from marine microfossils and terrestrial plant remains. Better dating techniques allowed scientists to constrain the timing of the warming event more precisely. Advanced drilling programs recovered sediment cores from locations that had previously been inaccessible. These improved datasets provided more granular information about how carbon sources and sinks changed during the PTM interval. The geological setting of the PETM offered important constraints on potential carbon sources. The event occurred during a time of active continental rifting and elevated volcanic activity in certain regions. Paleomagnetic studies traced patterns of magnetic mineral preservation that provided clues about environmental changes. Palynological investigations documented shifts in plant communities responding to warming and changing precipitation patterns. Paleontological evidence showed how marine microfossil assemblages reorganized in response to warming and ocean chemistry changes. Geochemical analysis of sedimentary sequences revealed variations in sulfur isotopes and trace metal concentrations. These elemental signatures reflected changes in oceanic oxygen levels and redox chemistry during the warming event. The distribution of different iron oxide minerals provided additional information about diagenetic processes and original depositional conditions. Careful interpretation of these varied signals allowed researchers to reconstruct environmental conditions with increasing sophistication. Alternative explanations for the carbon gap continued to emerge as research progressed into the 21st century. Some scientists highlighted the potential role of increased wildfire activity releasing carbon from terrestrial organic matter. Others emphasized the importance of permafrost thaw in Arctic and Antarctic regions, releasing previously sequestered carbon. Researchers investigated whether changes in ocean circulation could have mobilized dissolved carbon from deep water reservoirs. The possibility that multiple carbon sources contributed simultaneously gained increasing support from the research community. The PETM carbon gap has therefore persisted as an active research frontier. Contemporary studies employ cutting-edge analytical methods that were unavailable to earlier researchers. High-resolution isotopic records now allow scientists to track carbon cycling changes at decadal to centennial timescales. Sophisticated paleoclimate modeling incorporates improved understanding of atmospheric circulation and ocean dynamics. Integration of multiple independent datasets provides cross-validation and increased confidence in conclusions. The broader significance of resolving this carbon gap extends beyond academic interest in past climate change. Understanding rapid warming events archived in Earth's geological history informs our comprehension of climate system sensitivity. The PETM offers invaluable lessons about ecosystem resilience and adaptation during periods of environmental stress. Continued research addressing the carbon gap will refine models applicable to interpreting future climate scenarios. The field has not ignored the Webb results. That is important to say clearly. Multiple research groups have published serious attempts to reconcile the observations with the standard model, and some of them are genuinely clever. That matters. This is not a situation where the data came back and the institutions went quiet. The response has been active, published, and in many cases technically sophisticated. But active engagement and closing the gap are two different things. And after 3 years of serious work, the gap has not closed. What has happened instead is something more instructive. Each proposed fix works on the specific problem it targets and creates pressure somewhere else in the model. The anomaly does not disappear, it moves. The first explanation the field reached for was calibration error. The argument runs like this: redshift measurements, especially at extreme distances, carry uncertainty. Webb's initial photometric redshifts, estimates based on how light has shifted across different wavelength bands, could be overstated. Maybe some of these galaxies are not sitting at redshift 12 or 16. Maybe they are closer, younger, smaller, and the model survives intact. This is a reasonable first response to any unexpected observation. Instruments have systematic errors. Measurements get revised. Science is supposed to question its own readings before questioning its own frameworks. The problem is that the field then did exactly what it was supposed to do. Spectroscopic follow-ups came back. Spectroscopy is not an estimate. It resolves individual emission lines in a galaxy's light and pins the redshift with precision. For the most extreme objects, the ones most damaging to the standard model, those spectroscopic confirmations have held. The redshifts are real. The galaxies are where Webb said they were. The calibration exit is closed for the cases that matter most. So the field moved to the second explanation: efficient star formation. The argument here is that early galaxies were simply unusually productive, converting the available gas into stars at rates much higher than what the standard model's default efficiency parameters allow. The model does not specify a single fixed efficiency. There is a range. The early universe, the argument goes, may have sat at the extreme high end of that range. Dark matter halos assembled quickly, gas cooled fast. Feedback mechanisms that normally slow star formation were less developed. Stack those factors together, and you can, on paper, produce galaxies that look more massive than the standard timeline should allow. Some papers have made this case carefully, and the math is not obviously wrong. Here is the problem. The standard efficiency parameters are not arbitrary. They were set by observations across a very wide range of galaxy types, redshifts, and environments. When you push the early universe efficiency to the values needed to explain the most massive Webb detections, you are not using the parameter within its observed range, you are outside it. And when a model requires a parameter to operate outside the range the model was built on, that is not an explanation, that is a description. You are saying the observations are consistent with the model if the model is different from what it was. That is a different activity than making a prediction and having it confirmed. So, the third proposed fix is the most serious one. It is also the most expensive. The argument is that the early universe contained density fluctuations, regions of slightly higher and lower matter concentration that were larger than the standard model predicts. Structure formation in cosmology is seeded by those initial fluctuations. Gravity amplifies them over time, pulling matter into filaments and halos and eventually galaxies. If the seeds were bigger than expected, the structures that grew from them could have been bigger earlier. This is not an implausible mechanism, it connects to real physics. And unlike the efficiency argument, it does not require a parameter to operate outside its justified range. It requires the initial conditions themselves to be different. That is where the C-OST appears. The standard model's prediction of the initial density fluctuation spectrum is not a free parameter that can be adjusted without consequence. It is directly tied to the cosmic microwave background, the most precisely mapped dataset in cosmology. The CMB power spectrum is what it is. The fluctuation amplitude it implies is what it implies. If you need larger fluctuations to explain the early galaxies, you are in tension with the CMB. And the CMB is not a weak constraint. It is the foundational measurement the entire standard model was calibrated against. Giving up ground there is not a small concession. It pulls at the structure from a different direction than the Webb results pull at it from another. What you are left with is this. The calibration fix fails for the confirmed cases. The efficiency fix requires the model to operate outside its own observed range. The initial conditions fix relieves pressure at one point and applies it at another. None of these close the gap completely. Each of them, followed to its conclusion, requires changing something in the model that was not supposed to change. And the researchers doing this work are not making errors. They are skilled, the papers are peer-reviewed, the calculations are checked. The results are what they are because the problem is real, not because the proposed solutions are careless. That distinction is important. A gap that survives serious, competent attempts to close it is a different kind of gap than one that has simply not been studied enough. This one has been studied. The field's best tools have been applied to it. 3 years of targeted work have produced a collection of partial solutions, each technically defensible, none sufficient, all of them pointing in slightly different directions when you push them past their comfortable range. When every proposed fix requires adjusting a different fundamental parameter of the model, at some point, you are no longer fixing the model. You are describing a different model and calling it the same one. Here is the part that the Webb galaxy problem gets discussed without, which is a mistake, because without it, the cosmological crisis looks like a single unexpected observation that might have a simple fix. The Webb results are not the first crack. There was already a crack. It has been sitting in the published literature since roughly 2019, formally acknowledged, extensively studied, and not resolved. It is called the Hubble Tension. And before you can understand why the accumulating anomalies in cosmology are serious in the way they are serious, you need to understand what the Hubble tension actually is and why it has not gone away. The Hubble constant is a number. It describes how fast the universe is expanding, specifically how fast galaxies are receding from each other per unit of distance. The unit is kilometers per second per megaparsec. That sounds technical. The concept is not. The universe is expanding. Everything is moving away from everything else. The Hubble constant tells you the rate of that expansion. Get it right, and you get the age of the universe, the geometry of space, the entire timeline of cosmic history. Get it wrong, and everything downstream of it is wrong too. It is one of the most consequential numbers in all of science. There are 2 primary ways to measure it. They use completely different data, completely different instruments, completely different physics, and they give different answers. The first method looks at the early universe. The Planck satellite mapped the cosmic microwave background with extraordinary precision. The faint thermal radiation left over from roughly 380,000 years after the Big Bang, the oldest light we can observe. The pattern of that radiation encodes information about the density, geometry, and expansion rate of the early universe. Feed that data into the standard model and it produces a value for the Hubble constant. That number is approximately 67.4 kilometers per second per megaparsec. The second method looks at the late universe. Astronomers use a distance ladder, a sequence of overlapping measurement techniques that extend from nearby stars outward across billions of light years. At the far end of that ladder sit Type 1a supernovae. These are exploding stars with a known intrinsic brightness, which means you can calculate how far away they are from how bright they appear. Measure their recession velocity, measure their distance, divide. That produces a value for the Hubble constant. That number is approximately 73 kilometers per second per megaparsec. 67 versus 73. The difference is roughly 8%. That sounds small. It is not small. These are not rough estimates from early instruments. These are measurements that have been refined over years, checked against independent data, cross-verified by separate research groups using separate methodologies. The Planck result has been checked. The supernova result has been checked. The distance ladder has been examined for systematic errors repeatedly. The gap does not close. It has not narrowed meaningfully in 6 years of sustained effort. It sits there, statistically significant at roughly 5 sigma, which in physics means the probability this is a random fluctuation is negligible. 5 sigma is the threshold at which the field calls something a discovery. The Hubble Tension clears that bar. Here is what that means. The standard model, applied to the early universe, predicts an expansion rate. The standard model, applied to the late universe, predicts a different expansion rate. Same model, same universe. Different answers depending on which epoch you measure. That is not a situation where better instruments will close the gap. It is a situation where the model is internally inconsistent. Either something was different about the early universe than the CMB data implies, or something happened during cosmic evolution that altered the expansion rate in ways the standard model does not account for, or the model is missing something fundamental about how expansion works across cosmic time. None of those options is a small fix. The field has proposed explanations. Early dark energy, an additional component that briefly modified the expansion rate before recombination. New physics in the dark sector. Modified gravity. Revisions to how the distance ladder is calibrated at individual rungs. Each proposal handles part of the tension and generates new predictions that then have to be tested. None has resolved it. The tension remains open. It was open before Webb launched. It was open when Webb began returning data, and the Webb results arrived not as a replacement for the Hubble tension, but as an addition to it, a second structural problem compounding the first. That is the part that matters. 2 problems, not one. A single anomaly can be a measurement artifact, a poorly understood selection effect, a gap in some specific part of the model that needs patching. 2 separate anomalies, derived from independent data by independent methods, both pointing at inconsistencies in the same framework. That is a different situation. The Hubble tension was already there. The galaxy formation problem arrived on top of it. They do not have the same cause. They do not have the same proposed fixes. What they share is that the standard model, as currently constructed, cannot fully account for either of them. That is not a coincidence worth dismissing. It is a pattern worth examining directly. 2 independent measurement methods, both well-established, both repeat. Edley verified, producing incompatible answers about the same universe. That is not a calibration problem, that is a structural one. The most direct solution to the too big, too early problem is also the most uncomfortable one, which is why it appears in the literature with careful hedging and peer-reviewed qualifications rather than headlines. The proposal is straightforward. The universe is older than 13.8 billion years, not slightly older, significantly older. Rajendra Gupta, an astrophysicist at the University of Ottawa, published work in 2023 suggesting the universe may be approximately 26.7 billion years old. That is nearly twice the standard figure. He was not writing outside his field, not publishing in a fringe journal, not working from speculation. He ran the math against the same observational data the standard model uses and concluded that the timeline is wrong. His mechanism combines 2 things: a modification to how the cosmological coupling constants behave over time, and a revised version of tired light theory. The conclusion was peer-reviewed and published. It did not make the evening news. Tired light is worth understanding because it keeps reappearing in these discussions, and the field keeps dismissing it, and the dismissals keep running into problems. The basic idea is this: light loses energy as it travels, not because the universe is expanding and stretching the wavelength, which is the standard explanation for redshift, but because photons interact with something in the medium over cosmological distances. The further the light travels, the more energy it loses, the more redshifted it appears. If that is true, then redshift is not purely a distance and expansion measurement. It is also a travel time measurement, and the relationship between redshift and distance changes. Objects we place at extreme distances based on their redshift may be closer than we think, or the univ. Earth may be older than we think, or both. The standard model rejected tired light decades ago. The rejection was based on real problems. Tired light predicts that distant supernovae should look a certain way, and they do not look that way. It predicts that the cosmic microwave background should have a different structure than it has. These are not small objections. They are data-based objections, and they are why tired light fell out of mainstream cosmology in the 1990s. Here is the problem. Gupta is not proposing pure tired light. He is proposing a hybrid framework. Modified coupling constants plus tired light together produce a model that fits the CMB data and fits the galaxy formation data better than either mechanism alone. The objections to classical tired light do not automatically apply to the hybrid. Does the hybrid model work? That is an open question. It has critics. Some of those critiques are published, some are not. But the framework is not obviously broken in the way classical tired light was, and that distinction matters. What would it actually mean if the universe is 26 billion years old? Start with the problem the Webb results created. Galaxies forming too large, too early, in the first few 100 million years after the Big Bang. That is a problem because the standard model gives you roughly 300 to 500 million years to build those structures from near-uniform plasma. The physics of gravitational collapse at those scales requires time. There is no shortcut. If the universe is 26 billion years old, the early structures Webb is seeing formed at what the standard model calls redshift 12 or 15, but what a 26 billion year timeline places at over a billion years post-origin. Not 300 million, not 500 million, over a billion. The too big too early problem dissolves. The structures had time to form. The anomaly disappears. Except it does not disappear. It moves. Give the universe more time and you have to explain what it was doing with that time. The CMB is the record of the universe at roughly 380,000 years after the Big Bang, when the plasma cooled enough for light to travel freely for the first time. That record is not consistent with a universe that is 26 billion years old under a standard expansion history. The temperature fluctuations in the CMB, the acoustic peaks, the angular scale of those peaks, all of these encode the expansion history of the early universe. Change the age of the universe and you change the predictions for what the CMB should look like. The CMB data is some of the most precise data in all of cosmology. It is not easy to move. Gupta's model claims to fit the CMB. Other researchers have challenged that claim directly. The debate is in the literature, unresolved. That is the honest status. There are other proposals. Eric Lerner has argued for a plasma cosmology model with no Big Bang at all. Salvatore Capozziello and collaborators have worked on extended gravity theories that modify the expansion history without requiring dark energy. None of these are mainstream. None of them are obviously wrong in the way that would end the discussion cleanly. They are formal proposals from credentialed researchers sitting in the published record without sufficient follow-up from the institutions best positioned to test them. Here is what connects all of them. Every framework that tries to resolve the Webb galaxy problem by providing more time runs into the CMB. And every framework that tries to preserve the CMB runs into the Webb results. These are not independent problems pointing in the same direction. They are constraints pointing in opposite directions, and the space between them is where every proposed solution has to live. The gap does not close. It migrates from one corner of the model to another. That is the honest state of the field right now. Not a clean answer. Not one proposal that handles everything. multiple competing frameworks, each of which solves one piece and breaks another, each of which the mainstream has declined to pursue with the resources the question actually requires. An older universe solves one problem and inherits three others, which is either a sign that the idea is wrong or a sign that the entire framework it is being tested against needs to be replaced. Here is what the institutional response to a cosmological crisis looks like, because it does not look like what you might expect. It does not look like silence. That is the first thing to understand. The Silurian hypothesis came out. Two credentialed researchers published a formally modeled question, and the field responded with almost nothing. 7 years. No follow-up programs, no funded investigations, no serious attempt to verify the hypothesis using geological observations. That kind of silence was possible because the question was contained. It lived in a corner of astrobiology that most working scientists could ignore without professional consequence. The Webb results do not have that luxury. The images are public. The redshifts are confirmed. Hundreds of galaxies sitting where the standard model says almost nothing should be. You cannot quietly shelve that. So the response takes a different shape entirely. What it looks like from inside the literature is a proliferation of papers, dozens of them, serious work, carefully written, published in serious journals. Each one proposes a mechanism. Each one adjusts a parameter. Each one explains, in precise technical language, why the anomaly is probably not what it appears to be. Efficient star formation, revised dust models, selection effects in how the early universe is being sampled, redshift calibration uncertainties in the most extreme cases. The field is not ignoring the problem. It is surrounding the problem with explanations at a rate that should itself tell you something. When a result is clearly wrong, you get one paper correcting it. When a result is genuinely threatening, you get 30 papers negotiating with it. Here is the part that requires attention. Watch the language, not the conclusions. The language. In the published literature, the Webb galaxy problem is described as a tension, a challenge, a puzzle, an unexpected finding requiring further investigation. These are not synonyms for falsification. They carry a specific implication, which is that the model is under stress but still standing, that more data will clarify things, that the gap will eventually be closed without requiring anything structural to change. Calling something a tension is a different professional act than calling it a falsification. A tension asks for patience. A falsification asks for a replacement. And the field has chosen tension consistently across every paper that has engaged seriously with what Webb is returning. Why does the language choice matter? Because it shapes what happens next. If the anomaly is framed as a tension, the institutional response is to continue working inside the existing framework. Run more simulations, refine the parameters, wait for more data. The model survives. If the anomaly is framed as a falsification, the institutional response has to be different. You need a new model. You need to account for what the old one got wrong. You need to explain why 50 years of supporting observations pointed toward a framework that turns out to be incomplete at the earliest times. Those are different careers, different grant applications, different conference presentations, different professional identities. The language is not neutral, it is load-bearing. Now look at who built this model. Lambda-CDM was not assembled last decade. The foundational work spans 50 years. The researchers who developed its core predictions, who worked through the mathematics of structure formation, who matched its outputs to the cosmic microwave background data with extraordinary precision, many of them are still active. Their students are leading research groups. Their students are writing the papers that are currently negotiating with the Webb results. The institution has a generational depth that the data alone cannot overcome in a short period of time. This is not unique to cosmology. The same structure appeared in the Younger Dryas impact debate. The same structure appeared in the slow acceptance of plate tectonics. Paradigms do not fall when the anomalies appear. They fall when the generation that built them stops being the generation making the decisions. Consider the career calculus directly. A researcher who stands up at a major conference and states that Lambda-CDM is foundationally wrong, not stressed, not challenged, wrong, is making a paradigm-level claim. If they are right, they will not be credited for it for years, possibly decades. If they are wrong, the professional damage is immediate and lasting. The asymmetry is the same one that kept researchers quiet about the Silurian hypothesis. the same one that keeps anomalies sitting in footnotes for 30 years. Ask the question and get it wrong, and your credibility takes a hit it may not recover from. Say nothing and continue publishing inside the established framework, and nothing happens to you personally. The incentive structure does not reward honesty about paradigm failure. It rewards caution. So what this produces, in practice, is a literature that is technically rigorous and collectively evasive. Every individual paper is doing real science. Every proposed fix is a serious attempt at an explanation. The evasion is not in any single paper. It is in the aggregate. It is in the fact that the sum of all those careful explanations still does not close the gap, and the direct conclusion that the gap itself implies is not being stated anywhere with institutional weight behind it. The data is there, the pattern is legible. The conclusion sits at the end of a short logical chain that the field has declined to walk to the end of. Calling something attention is a way of saying the model is stressed without saying the model is broken, and the difference between those two statements is the difference between a field that is about to update and a field that is waiting for the generation that built the consensus to retire. There is a history to this that matters, because the Webb galaxy problem is not the first time the standard model of cosmology has encountered observations that its equations could not explain without adjustment. The model has a pattern. It is not a hidden pattern. It is documented in the literature, acknowledged by the researchers who built the framework, and taught in graduate programs as an example of scientific adaptability. When the standard model encounters an observation its equations cannot produce, the field does not typically discard the equations. It adds something, an invisible component, a new parameter, something that, when inserted into the mathematics, makes the prediction match the data. This has happened twice at the largest scale in modern cosmology, and both times it worked mathematically, and both times the physical thing that was added has never been found. That is not a minor footnote. That is the structure of the model. Start with dark matter. In the 1970s, astronomers measuring the rotational speeds of galaxies found a problem. Stars at the outer edges of galaxies were moving too fast. Under the standard distribution of visible mass, those stars should not be moving that fast. Gravity from the visible material was not strong enough to hold them in their orbits at those speeds. Either the physics of gravity was wrong at galactic scales, or there was mass that nobody could see. The field chose the second option. Dark matter was proposed as a substance that does not emit or absorb light, exists in halos surrounding galaxies, and provides the gravitational mass that the rotation curves require. The math worked, the curves matched, the model was preserved. 50 years later, dark matter has not been detected, not once. Particle physicists have run experiments in deep underground laboratories specifically designed to catch dark matter interactions. They have found nothing. Collider experiments at energies that should have produced dark matter candidates have produced nothing. The detection programs have been refined, expanded, and repeated. The result is the same. The math requires it. The instruments cannot find it. Then, in 1998, two independent research teams measuring the distances to Type 1a supernovae found something worse. The expansion of the universe was not slowing down. It was accelerating. The standard model predicted deceleration. Gravity should have been pulling the expansion back. Instead, something was pushing it forward, and the push was getting stronger over time. Again, the field had two options: revise the foundational equations, or add something invisible. Again, the field added something invisible. Dark energy was proposed as a property of space itself, a repulsive force distributed uniformly through the vacuum, driving the accelerating expansion. The math worked. The Nobel Prize followed in 2011. The physical nature of dark energy remains completely unknown. Together, dark matter and dark energy account for roughly 95% of the total mass-energy content of the universe according to the standard model. The remaining 5% is everything that has ever been observed, measured, touched, detected, or confirmed by any instrument ever built. The model that describes the full history and structure of the cosmos is, by its own accounting, 95% composed of things that exist only as inferences, things that were added because without them the predictions fail. Here is what that history tells you about the model's instincts. When the data does not match, the model adds. It does not question the foundational assumptions about how the universe began, how gravity operates at large scales, or what the initial conditions of cosmic structure formation actually were. It adds a component. It makes the math work. It moves forward. That process is not dishonest. In both cases, the proposed additions were falsifiable in principle, which is the scientific requirement. The problem is that decades of direct detection attempts have not falsified them, but have also not confirmed them, and the model has continued regardless. Now Webb is producing a new category of anomaly: galaxies too massive, too structured, too early. The same framework that absorbed two previous crises by addition is now facing a third one. And the question that the history forces into the open is whether the field's next move will follow the same pattern, whether there will be a new component, a new parameter, a new invisible addition that makes the equations produce massive early galaxies without requiring a revision to the foundational timeline. Some proposals are already moving in that direction: modified star formation efficiency, early dark energy variance, primordial black holes seeding structure formation faster than the standard model allows. Each proposal preserves the core architecture of Lambda-CDM and patches the specific prediction that Webb is breaking. Each proposal requires inserting something that was not in the original model. The pattern is recognizable. This is not evidence that the model is wrong. Dark matter and dark energy were genuinely productive additions in scientific terms. The predictions they enabled were tested extensively and largely held. The model is not obviously broken just because it has been extended. But there is a difference between extending a model because new phenomena have been discovered and extending a model because the existing predictions keep failing. The first is how science builds. The second is how science stalls. After the Hubble tension, after the Webb galaxies, after 50 years of failed dark matter detection and 25 years of unexplained dark energy, the cumulative weight of the additions is a meaningful data point about the model's foundations. Not proof of failure, a signal worth reading honestly. A model that is 95% composed of components that have never been directly observed is not wrong by definition, but it is worth asking at what point the additions stop being refinements and start being a different kind of answer entirely. What makes the Webb results different from every previous cosmological anomaly is not just the magnitude of the discrepancy, it is where the observations are coming from. Webb is not looking at the middle distance. It is not catching galaxies from a few billion years ago, in an era where the universe was already structured and familiar. It is looking at light that has been traveling for over 13 billion years, light that left its source when the universe was less than 400 million years old. In some cases, less than 300 million years old. That number needs to sit for a moment. The universe is approximately 13.8 billion years old by the current model. Webb is observing the first 2 to 3% of cosmic history, not the early universe in the loose sense that phrase gets used, the literal opening interval, the period when the first structures were only just beginning to pull themselves out of near uniform darkness. Before those first stars ignited, there was no light, not dim light, not distant light, no light at all. The universe was filled with a fog of neutral hydrogen, opaque to the photons that would eventually become visible radiation. This period has a name. Cosmologists call it the Cosmic Dark Ages. It ran from roughly 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral atoms, all the way until the first stars formed and began pumping out ultraviolet radiation intense enough to strip those atoms apart again. That second process is called rionization. It is the moment when the universe became transparent, when light became possible as a traveling thing, crossing distances, carrying information, eventually arriving at a detector 13 billion years later. Webb is operating at the edge of that boundary. It is probing the era right at the end of the cosmic dark ages, when rionization was beginning or had just completed, when the first coherent sources of light were switching on across the universe for the first time. There is a wall behind that boundary, not a metaphorical wall, a physical one. Before rionization, the universe was opaque. No light from that era can reach us. It was absorbed before it could travel, which means there is a hard observational limit to how far back any telescope can see, regardless of how powerful it is, regardless of how long it collects photons. That limit is set by physics, by the speed of light, the age of the universe, and the transparency threshold of the early cosmos. Webb is working right up against that limit, And at that limit, it is finding galaxies, massive ones, structured ones, galaxies with stellar masses that required significant time to assemble, sitting in an era when there was almost no time available. That is the specific shape of the problem. It is not that Webb found something faintly unusual in the middle distance. It is that Webb looked at the farthest edge of what any instrument can physically observe, the boundary where light itself only recently became possible, and found the wrong thing there. This is worth being precise about. The cosmic dark ages ended somewhere between 150 million and 800 million years after the Big Bang. The exact timeline is itself a subject of active research, but the galaxies Webb is identifying at redshifts of 10, 12, and higher correspond to periods well within that window. Some candidates push toward periods when reionization was not yet complete, when significant regions of the universe were still opaque. These objects should not be mature, they should not be massive. By the Standard Model's timeline of structure formation, they should barely exist. What does it mean, physically, to look at light from 300 million years after the Big Bang? It means you are receiving a signal that was emitted when our sun did not exist, when the Milky Way did not exist, when the entire scaffold of the familiar universe had not yet been constructed. The photons arriving at Webb's mirror left their source before any of the structures we consider normal in the universe had time to form. They have been traveling through expanding space ever since. The universe stretched around them as they moved. Their wavelengths stretched with it. By the time they arrive, they are infrared light, shifted from ultraviolet by 13 billion years of cosmic expansion. Webb was specifically built to detect that shifted light. It was built to see exactly this far. And now that it is seeing this far, what it is finding is not what the people who built it predicted. This is not noise. It is not calibration drift. It is not an artifact of the detection process. Spectroscopic follow-up observations have confirmed the redshifts on multiple objects. The distances are real. The masses being inferred are real within the uncertainty ranges. A telescope built to observe the boundary of the observable universe is observing that boundary, and the objects there are the wrong size, the wrong mass, the wrong degree of organization for the time the model assigns to that place. The edge of the observable universe is not a metaphor. It is a physical boundary set by the speed of light and the age of time itself, and what Webb is finding there does not match what the math says should exist. Here is the pattern, stated plainly, because it has appeared enough times now that naming it is not paranoia, it is just reading the record. The PETM carbon fingerprint. Biological origin confirmed. Volume exceeding every known natural source. 30 years of open literature and no closed explanation. The Younger Dryas impact evidence. A continent-wide layer of shocked minerals, nanodiamonds, iridium, and melted glass beads deposited simultaneously across 4 continents. Published, contested, studied extensively. No settled conclusion. The Silurian hypothesis. 2 credentialed NASA-affiliated scientists formally model what a prior industrial civilization would leave in the geological record, then note that the record contains exactly that signal, published in a peer-reviewed journal. Covered briefly, then silence. The Hubble Tension. 2 independent measurement methods, both verified repeatedly, producing incompatible numbers for the expansion rate of the same universe. Known since 2019. Still unresolved. The Webb galaxy problem. Hundreds of massive, fully formed galaxies appearing in the first few 100 million years of cosmic history, in direct contradiction to what the Standard Model predicts. Confirmed by spectroscopic follow-up, still not explained. Different fields, different timescales, different instruments, different data sets, different researchers, same structure every time, anomaly detected, anomaly named, anomaly studied at length, direct conclusion avoided. That is not a coincidence. It is a pattern, and patterns in data are supposed to mean something. Here is what makes this particular pattern worth examining carefully. These are not fringe fields. Geology, archaeology, and cosmology are 3 of the most heavily funded, most methodologically rigorous disciplines in all of science. They are also, without exception, the 3 fields most directly concerned with reconstructing what existed before the current moment, before human civilization, before the solar system as it currently exists, before the universe as we currently observe it. They are the fields whose entire purpose is to look backward and describe what was there. And in each of them, when the data points clearly toward a conclusion that would require revising the foundational framework, the field stops just short of stating that conclusion directly. Why those three fields specifically? That question is worth sitting with. There are two possible answers. The first is that this is simply how science works at the paradigm level. Large, well-established frameworks generate enormous institutional momentum. Researchers build careers on them. Graduate programs are structured around them. Funding flows through them. When an anomaly appears, the rational response for any individual researcher is to look for a small fix rather than propose a foundational revision, because the professional cost of being wrong about a paradigm-level claim is asymmetric and permanent, while the cost of staying quiet is zero. The pattern repeats not because the fields are suppressing something, but because that is what institutional science does when it encounters data it cannot yet integrate. The anomalies accumulate until the framework finally breaks, and then it breaks all at once, and everyone later describes the preceding period as obvious in retrospect. That is a coherent answer. It fits the history of science. It requires no additional explanation. The second answer is harder to state without sounding like something other than what it is, which is a serious question. What if the pattern repeats specifically in those three fields, because those three fields are the ones most likely to find something that genuinely unsettles the assumed history of this planet and this universe? The PETM anomaly points at a prior industrial event. The Younger Dryas evidence points at a catastrophic impact that reshaped a civilization. The Silurian hypothesis points at the possibility that intelligent life preceded us here. The Webb results point at a universe older and more structured than the timeline allows. Each of these, if followed to its direct implication, does not just revise a model. It revises the story of what came before us and how we arrived at this moment. That is a different kind of uncomfortable than a calibration error in a redshift measurement. And the institutional response is proportionally different every single time. Is the pattern a feature of how science works, or a feature of what science finds when it looks carefully at the deep past? The honest answer is that both explanations account for what we observe. The honest answer is also that one of them is significantly more disturbing than the other, and the field most qualified to distinguish between them has not attempted to do so. Not formally, not directly. The data keeps returning the same structure. The gap keeps sitting open in the published literature. The direct conclusion keeps going unstated. The question of whether that pattern is how science works, or what science finds when it looks at the deep past, has two very different answers, and nobody in a position of institutional authority has been willing to state either one directly. Take the possibility seriously for a moment, not as a rhetorical exercise but as a physical question. What actually follows if Lambda-CDM is wrong in a foundational way? Not slightly off, not correctable with a tuned parameter or a revised efficiency estimate. Wrong in the way that means you cannot patch it, you have to replace it. What does that actually require? Start with the timeline. The 13.8 billion year age of the universe is not a raw measurement, it is a derived number. Feed the CMB data into Lambda-CDM and the model returns 13.8 billion years. If the model is wrong, that number is not confirmed. It is the model's answer to its own question. A different framework with a different expansion history gives you a different age. That age could be older. The timeline of cosmic history, from the first fraction of a second through recombination through the cosmic dark ages through rionization, is built on that foundation. If the foundation shifts, every date on that timeline shifts with it. Structure formation goes next. The entire account of how matter organized itself, how filaments formed, how halos collapsed, how the first stars ignited, is a prediction of the model. The model says small structures first, large structures later, assembled hierarchically over billions of years. That sequence is what Webb is observing at z equals 10, z equals 12, z equals 16, and finding violated. If the model is wrong about the timeline, it may be wrong about the sequence. The physics of how gas collapses under gravity does not change, but when it collapses, at what density, seeded by what initial conditions, those answers come from the model. They would need to be rebuilt from the observations rather than derived from first principles that have already been assumed. The CMB interpretation is the most complicated piece. The cosmic microwave background is real. The signal is real. Every satellite that has measured it has returned consistent data, but the CMB is not self-interpreting. The power spectrum, the pattern of temperature fluctuations across the sky, is read through the lens of the standard model. The model tells you what the peaks mean, what the spacing between them implies about the density of baryonic matter, and dark energy. A different model produces a different reading of the same signal. The CMB does not disappear if Lambda-CDM is wrong. Its interpretation does. Here is what does not need to be rebuilt. The laws of physics, nuclear fusion in stellar cores, the confirmed abundance of light elements produced in the first minutes after the Big Bang, the expansion of the universe, which is directly observed, not modeled, gravitational lensing, the formation of stars and planetary systems at scales the model has always described well. Lambda-CDM works. At intermediate scales, at late cosmic times, across the billions of years of history that existing telescopes could reach before Webb, it produces accurate predictions. That track record is real. Discarding it entirely is not what a model replacement requires. This is where the historical precedent matters. Newtonian gravity was not wrong. For every application it had been used for, planetary orbits, projectile motion, tidal forces, it returned correct predictions. General relativity did not falsify it. General relativity showed that Newtonian gravity is what you get when velocities are low and gravitational fields are weak. A limiting case, accurate inside its domain of applicability, incomplete outside it. The transition from Newton to Einstein did not erase 2 centuries of physics. It explained why 2 centuries of physics worked and then extended the description further. Lambda-CDM may be sitting in exactly that position right now, accurate inside its domain, incomplete at the edges, literally at the edges, at the highest redshifts, at the earliest times, at the boundary conditions where the model was always least tested and where Webb is now measuring for the first time. The framework that replaces it, if one is required, would not discard what Lambda-CDM gets right. It would explain why Lambda-CDM gets those things right and then describe what Lambda-CDM cannot. That is not a catastrophe. That is the normal motion of physics. Every major framework transition in the history of science followed that pattern. The question is how long the transition takes and whether the field in the middle of it can acknowledge what the data is showing before the anomalies become impossible to reframe as tensions. What makes this moment different from previous transitions is the instrument. Webb is not going away. It will operate for decades. Every year it returns more data from the same region of the sky where the anomalies are concentrated. If the galaxies at z equals 12 are real, and spectroscopic confirmation on multiple objects says they are, then more observations will not make the problem smaller. They will make it larger and more specific. The model will face an accumulating record of contradictions rather than a single surprising result that might resolve itself. The field knows this. The researchers publishing the small fixes know this. Nobody working at the edge of the observable universe genuinely believes that one more calibration adjustment closes the gap. What they believe, or what the publication record suggests they believe, is that someone else will close it, or that the data will eventually clarify, or that the problem belongs to the next generation to name directly. A wrong cosmological model does not break physics. It means the framework we built to describe the largest scales and earliest times is a limiting case of something more complete, which is either terrifying or exactly how science is supposed to work, depending on whether your career is built on the current framework. Here is the honest state of this, without the careful language the papers use. We are not looking at this from a safe distance. The crisis is not historical. It is active, running in real time, inside the journals and the conference rooms, and the gap between what Webb returns and what the equations say should be there. Future cosmologists will study this period the way we study the years before every major paradigm shift, not as a moment of discovery, as a moment when the data was already pointing somewhere and the field was slow to follow. That is not an accusation. It is a description of how this has worked every time before. The carbon fingerprint at 56 million years had the same structure, an anomaly, documented, named, studied in careful detail, and the direct conclusion avoided. The Hubble tension followed the same shape. 2 measurements of the same universe producing incompatible numbers. 5 years of papers calling it a tension. No resolution. The Webb results arrived on top of that, and the language did not change. Tensions, challenges, further research needed. Here is what that language does. It keeps the question open without requiring the field to answer it. It allows the anomaly to sit in the literature indefinitely without forcing the conclusion that the model may be wrong. And every year it sits there, the data gets stronger. Spectroscopic confirmations have locked in redshifts that should not be possible. The galaxies are real, the distances are confirmed, the stellar masses are measured. The problem is not an instrument error. It is not a software artifact. It is the sky. Webb will keep operating, possibly for 20 more years. Each new observing cycle will return more data from earlier times, higher redshifts, deeper into the period the model was most confident about predicting. Every one of those results will either deepen what we are already seeing or begin to pull it back towards something the standard model can absorb. What none of it will do is leave the model unchanged. That part is already decided. The question is only how large the change has to be. The honest answer to what this all means is that we do not know yet. Not fully. The data is pointing at something, and the field is still deciding whether to follow it directly or to keep adjusting parameters until the numbers look acceptable. Those are two different activities. One of them is science. The other is the performance of science, the appearance of rigor without the willingness to accept what the rigor actually shows. What makes this moment different from earlier anomalies is that Webb is not a subtle instrument. It is the most capable observational tool humanity has ever pointed at the sky. The results are not marginal. They are not sitting at the edge of statistical significance. They are galaxies, hundreds of them, fully assembled, too large, too early, at the literal boundary of observable time, in the first few 100 million years after the Big Bang, doing something that the most precisely tested model in the history of physics says they should not be doing yet. Something at the edge of time is not behaving the way it should, and the only intellectually honest response to that, the one that the data has been asking for since the first Webb deep field came back, is to follow it and see where it goes.